Swayam Prabha. Digital India. Educated India.
In the last class we looked at how to derive the shape functions for rectangular elements and square elements, and we discussed two kinds of elements. One is Lagrangian element and another one is serendipity elements. So basically here I want to summarize what we have done in the last class, and at the end of the last class we have seen a table in which a general set of functions are given to derive shape functions or to write the shape functions explicitly for 4 to 9 node rectangular element. And so this is the element that we are considering. All the nodes are numbered and the corresponding locations can be easily figured out from the figure that is given. And here node numbering is the way the nodes are numbered is very important, because with this particular node numbering scheme, shape functions for higher order elements can be constructed by adding terms into the shape function for lower order elements. And now a complete set of shape functions for any element with nodes from 4 to 9 are given in the table below. And before we read the table to get the shape function expressions for any noded element starting from 4 node to 9 node, certain functions are defined in terms of this coordinates of this element. So along x direction, if you see this element is of length, is having length of a units, and along y direction it has b units, and the coordinate system xy coordinate system is defined with respect to centroid of the element. So following notation is used: s is equal to 2x over a, y is equal to, or t is equal to 2y over b. So s and t are defined like this. With this definition of s and t, f1, f2, f3, f4, f5, f6, f7, f8, f9 are defined in terms of s and t, where s and t are obtained based on the coordinates of the particular element. So once f1 to f9 are defined like this, shape functions of 4 to 9 node rectangular elements can be written in terms of this f1 to f9. So table shows for 4 node element how the shape function expressions are related to these functions. Similarly 5 node element, 6 node element. So once we go through this table, we can easily write the explicit expressions for any noded element starting from 4 node to 9 node rectangular element. Similarly 7 node, 8 node element, and 9 node element. and elements with number of nodes between 4 and 8 are known as transition elements. And let us see where these transition elements are useful. They are useful when a transition from quadratic elements to linear elements is desired. Figure below shows proper transition from a mesh with 8 node elements to a mesh with 4 node elements through the use of 5 node transition elements. So, here you can see a part of mesh consists of 4 node elements and rest consists of 8 node elements, and in between the transition from 4 node to in the region where we have this transition, there 5 node element is adopted. And also now we will see what happens if we do not use these transition elements. Instead we can, if you take a mesh where we have 4 node element and immediately we have 8 node element, what happens? As illustrated in figure below, without the use of these transition elements, the trial solution is not continuous across element boundaries. That can be better, the statement can be better understood by taking this illustration here. So, 4 node element mesh is directly immediately connected with 8 node element mesh. So, if you can see the edge towards which the arrows are pointed out, you have linear solution on one side towards the side of 4 noded elements. You have a linear solution in terms of nodes 1 and 3, and whereas on the side where 8 node elements are present, quadratic solution in terms of nodes 1, 2, 3. So, this violates one of the basic mathematical requirements, which lets us evaluate integrals over elements and then sum these integrals to get integrated quantities for the entire domain. So, the mathematical requirement that it violates is the solution variation in each of these elements along the same edge is different. So, to avoid this kind of mathematical violations, we usually adopt transition elements. Now, let us look at how to derive shape functions for a 5 node element. A 5 node element is shown here. If you compare the node numbering that is given here with the node numbering that we have seen when before we looked at the table, which gives us shape functions for 4 to 9 node elements. And if you compare these two node numberings of these two elements, you can see the node numbering is similar to what we have seen earlier. So, we can directly use the expressions that we have for 5 node element and plug in the corresponding nodal coordinates, and we can get the shape function expressions for this particular element. For this element, A is equal to 4 units, B is equal to 2 units, therefore, S is equal to x over 2 and t is equal to y. So, once we have s and t, from the general formula the shape functions for a 5 node element are as given here n1, n2, n3, n4 and 5. Basically these expressions are written taking from the table that I just showed you before. So, n1 to n5 can be obtained once we substitute s and t in terms of x and y, and we just calculated using the information that is given, the nodal coordinate information that is given for this particular element, how s is related to x, that is s is equal to x over 2, y is equal, t is same as y or t is equal to y. So, substituting that into these expressions n1 to n5, we get shape functions for this particular element. Substituting s and t values into the above shape function formulas, the explicit expressions for shape functions for 5 node rectangular element can be obtained as given here n1, n2, n3 in terms of x and y, n5, n1 to n5. And we can also plot this if one wants to see, visualize how these shape functions look when they are plotted with respect to x and y. X going from -2 to -2 to 2, y going from -1 to 1. So, 3 dimensional plots of 2 of the shape functions, namely n3 and n5 are shown, and this is how n3 varies over the domain of that particular element, and this is how n5 varies. So, for any other noded element, that is 7 noded element for example, can be easily obtained from the table. So, now let us go to the other concept, isoparametric mapping for quadrilateral elements. If you recall, we have already looked at this when we are dealing with one dimensional problems. The basic concept of isoparametric elements was introduced earlier in the context of one dimensional problems. Essentially the same idea applies to 2 and 3 dimensional problems. Only thing is, the parent element for 2 dimensional problem is a 2 by 2 square defined in terms of s and t with origin at the center and s going from -1 to 1, t going from -1 to 1. Nodes are placed symmetrically on the parent element. To get an idea, here these are 2 elements, one is 4 noded element and other one is 8 noded element, and both are actual elements, and these elements in isoparametric mapping we are going to map onto parent element like this. The 4 noded element is going to be mapped onto a parent element having 4 nodes, nodes 1 to 4, and the nodal coordinates are also indicated, and an 8 noded element is going to be mapped onto an 8 node parent element. and the nodal coordinates can be easily figured out from the information that is given in the figure. So, in isoparametric mapping, for if you recall what we did for one dimensional problems, shape functions are defined in terms of parent element coordinates. So, same thing we will be doing here also for two dimensional problems. Shape functions are defined in terms of parent element coordinates. Then geometry of actual element is mapped onto the parent element using these shape functions. If you recall, earlier we have written x is equal to sigma ni times xi for one dimensional problem. Similar kind of expressions we can write for two dimensional problem, except that for two dimensional problem we have x and y coordinate system. Thus, the mapping from physical coordinates x, y to parent element coordinates s and t is given by the following equations. X as a function of s and t is equal to sigma times ni as a function of s and t times xi. Similarly, y as a function of s and t is equal to sigma ni as a function of s and t multiplied by yi, where xi and yi are the nodal coordinates of the actual element. So, shape functions are defined in terms of parent element coordinates, xi and yi are nodal coordinates of actual elements. So, this is how physical coordinates x, y are mapped onto the parent element coordinates s and t. And also during the derivation of finite element equations, derivatives of shape functions with respect to x and y are required. Since shape functions are defined in terms of parent element coordinates, we can easily find what is the derivative of shape function with respect to s and t, and once we get shape functions derivatives in with respect to s and t, we can find shape function derivatives with respect to x and y using chain rule. Since shape functions are actually written in terms of s and t, chain rule of differentiation must be used to obtain the desired derivatives, that is partial derivative of ni, I takes values depending on the number of nodes that a particular element has. So, partial derivative of shape function with respect to s can be written as partial derivative of shape function with respect to x times partial derivative of x with respect to s plus partial derivative of shape function with respect to y times partial derivative of y with respect to s. Similarly, partial derivative of shape function with respect to t is equal to partial derivative of shape function with respect to x times partial derivative of x with respect to t plus partial derivative of shape function with respect to y times partial derivative of y with respect to t. These two equations can be written, or we can put these two equations in a matrix and vector form. Writing the two equations in matrix form, we get this, where a new quantity or a quantity which you are already familiar with, which is called Jacobian. You are familiar with Jacobian for one dimensional elements, Jacobian there for one dimensional elements is defined as dx over ds, if you can recall. For two dimensional elements, Jacobian becomes a matrix, that is why J is written in matrix notation, that is bold letter, where 2 by 2 J 2 by 2 matrix J is called Jacobian matrix and its determinant is called Jacobian. We have this relation if we know the derivatives of shape function with respect to s and t, we can easily find what is the derivative of shape function with respect to x and y and vice versa. And here if you see this equation, if we know the derivatives of shape function with respect to x and y, and this relation gives shape function derivatives with respect to s and t, and if we invert this by inverting Jacobian matrix, the derivatives with respect to x and y can be obtained. So, this is the inverse relation, that is derivatives of shape function with respect to x and y are expressed in terms of derivatives of shape function with respect to s and t, for which we require inverse of Jacobian, which is given there, where determinant of J, determinant of Jacobian is defined like this: partial derivative of x with respect to s times partial derivative of y with respect to t minus partial derivative of x with respect to t times partial derivative of y with respect to s. So, basically what we did is we mapped the physical coordinates x, y to parent element coordinates s and t, and from there we got all this. For that mapping to be valid, any point in the actual element should correspond to a unique point in the parent element. So, for the mapping from physical coordinate system x y to the parent element coordinate system s and t to be valid, any point in the actual element should correspond to a unique point in the parent element. With the given mapping, it is easy to see that corners of actual element are mapped to the corresponding corners of parent element. To illustrate this, let us go back to the figure which we have already seen and verify whether this statement is correct or not. What this statement says is corners of actual element are mapped to the corresponding corners of parent element. Let us check whether this statement is true or not. So, these are the two actual elements, one is 4 node element, another is 8 node element. These elements are mapped onto these parent elements, corresponding parent element. 4 node element is mapped onto 4 node parent element, 8 node element is mapped onto 8 node parent element. And if you take node 1 in any of these elements, node 1 corresponds to s is equal to -1, t is equal to -1, and at node 1 only n1 is non-zero shape functions, which means that s, recall how x is defined, x is sigma ni xi. So, all other shape function values at node 1 are 0 except node 1, which is equal to 1. So, x becomes same as x1 and y becomes same as y1. So, that is what that statement says. For example, at node 1 only n1 is non-zero shape function, and actually it is non-zero and its value is equal to 1, which means that x evaluated at s is equal to -1, t is equal to -1 is x1, and y evaluated at s is equal to -1, t is equal to -1 is y1. So, this verifies, or this illustrates, that corners of actual element are mapped onto corresponding corners of parent element. For the interior of the element, so corner nodes no problem, they are mapped, but for interior of element to be mapped properly, Jacobian, that is determinant of Jacobian, must not be 0 anywhere over the element. So, this is the requirement. Mathematically, the reason for this requirement can be seen from the fact that Jacobian appears in the denominator in the equations for computing derivatives. If you recall the relation to get the derivatives of shape function with respect to x y, we are required to find what is 1 over determinant of j. So, that is what this statement says. Mathematically, the reason for this can be seen from the fact that Jacobian appears in the denominator in the equation for computing derivatives with respect to x and y. So, if that is equal to 0, that is determinant of j is equal to 0 anywhere over the domain of the parent element is s going from -1 to 1, t going from -1 to 1, then the derivative at that point cannot be evaluated and mapping is not useful, because 1 over 0 is infinity. So, we cannot find derivative at that point, and mapping is not going to be useful. And we will illustrate these issues related to mapping by considering some numerical examples. So, now let us take an example, numerical example. Check the validity of isoparametric mapping for 4 node quadrilateral element shown here. This is the 4 node quadrilateral element. In the figure, the nodal coordinates are given, and we can easily figure out what are x1 to x4 and y1 to y4. And before we proceed with writing the expressions for mapping, we need to know what are the shape functions for a 4 node parent element in terms of s and t. So, consider a 4 node quadrilateral element shown here in the first figure. The coordinates of node 1 to node 1 are x1 y1, and for node 2 x2 y2, similarly for other nodes. The square element shown in first figure or figure A is mapped onto the parent element, which is shown in figure B. The square element, so the square element shown in figure B is used as a parent element for the actual element shown in figure A. Mapping from xy coordinates of the actual element to s and t coordinate is given by shape functions written in terms of parent element. So, now going back to the problem that we are looking at, the shape function for parent element are these n1 to n4 in terms of S and T, and we already noted down what are x1 to x4, y1 to y4. So, we can easily write what are the expressions for isoparametric mapping. X, how it is related to S and T is given by x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, where n1 to n4 n1 to n4 they are shape functions of the parent element which are given, and x1 to x4 are the nodal coordinates of the actual element. Similarly, y is equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4, where n1 to n4 are the parent element shape functions, y1 to y4 are the actual element nodal coordinates. Substituting this information, we get the relationship between y and S and T. So, once we get these two expressions, x in terms of S and T, y in terms of S and T, we can easily take partial derivatives of x with respect to S, partial derivative of x with respect to T, similarly partial derivative of y with respect to S, partial derivative of y with respect to T, and find what is J. And once we get J, we can find what is determinant of J. And one of the requirement is determinant of J should not be equal to 0 over the domain of the parent element, which is going from which goes from S minus 1 to 1, T going from minus 1 to 1. So, over this domain determinant of J should not be 0, or clearly we can verify that determinant of J expression that we obtained, we can easily check that is indeed is greater than 0 for the domain of the parent element, S going from minus 1 to 1, T going from minus 1 to 1. So, this mapping is good, thus isoparametric mapping is fine for the given element, and this is one way of checking mapping, that is once determinant of J expression is obtained, checking whether determinant of J is greater than 0 over the parent element domain. That is one way of checking whether mapping is fine or not. The other way of checking mapping is we already have x in terms of S and T, y in terms of S and T. We can plot this mapping can be seen more clearly by creating a plot using x, y from isoparametric mapping equations for different values of S and T. So, we have x in terms of S and T, y in terms of S and T. We can plot this over the parent element domain as going from minus 1 to 1, T going from minus 1 to 1 using some plotting software with little bit programming. One can use Mathematica or MATLAB to plot this, to get this plot. So, we have these expressions, plot these expressions between S going from minus 1 to 1, T going from minus 1 to 1. So, if we do that, we get a plot like this, and here you can easily see that if you compare this plot with the actual element, this is exactly same as actual element. So, when this figure is compared to the actual element, it clearly shows that mapping is correct. So, this is how one can check validity of isoparametric mapping. So, we have taken a 4 noded element and we verified for the element we have taken, mapping turned out to be fine, But now let us take another element and see when mapping is going to be not good or when there is going to be some problem with mapping. So, now let us take an example, check the validity of isoparametric mapping for 4 node quadrilateral element is looking like this. So, before we proceed, or we need to follow same steps as we did for the last example. So, before we proceed further, we just make a note of all the x coordinates and y coordinates of all the nodes of parent element, x1 to x4, y1 to y4, and using parent element shape functions, that is shape functions corresponding to a 4 node element in parent coordinate system S and T, and using these coordinates x y of all the nodes, we can write isoparametric mapping x in terms of S and T, y in terms of S and T. Once we get these two expressions, we can easily take partial derivatives with respect to S and T, and we can find what is determinant of J, and determinant of J is given by this. And now our job is to check whether determinant of J is greater than 0 over the parent element domain, as going from -1 to 1, T going from -1 to 1. Instead of that, we can check when determinant is going to be determinant of J is going to be 0 by looking carefully at this expression. So, now let us equate determinant of J to 0. Note that determinant of J is equal to 0 when 3 over 2 minus 15 S over 4 plus 15 T over 4 is equal to 0. So, that results in the line S minus T is equal to 2 over 5. And if you plot, if you overlay this line, that is S minus T is equal to 2 over 5 on the parent element, you can easily see that this is going to, this line is going to cut across the domain of the parent element, which is going from S minus 1 to 1, T from minus 1 to 1. So, you can easily verify when you plot this, when we overlay this line over the parent element, this line is going to cut across that particular element. So, in that case, at some point on that element or some point inside the element, Jacobian or determinant of J is going to be 0. So, this is one another way of checking. Earlier we checked whether determinant of J is greater than 0 over the parent element domain, and here we are actually checking where determinant of J is equal to 0 along what line, and we are overlaying that line on the parent element domain, and that is also another way of checking whether mapping is good or not. So, here in this case it turns out that mapping is not good, because determinant of J changes sign across the line, which is going to cut the element domain. So, it is going to be determinant of J is going to be 0 along this line, S minus T is equal to 2 over 5. So, mapping is not good. And also we can plot, this is one way of checking mapping, that is using determinant of J. The other way is we can plot x and y using MATLAB or Mathematica with a little bit programming. So, if you plot x and y over the element domain S going from -1 to 1, T going from -1 to 1, you can easily see that a part of element is folded onto itself. So, this kind of thing is not acceptable, because every point in the actual element maps are required to be mapped onto a unique element in the parent element, and when this kind of folding is happening, that means it is violating that requirement. So, mapping is not good. So, this is another way of checking by plotting x and y with respect to s and t. So, this particular element mapping is not good. So, now let us see how to check validity of isoparametric mapping for 8 node element. This is the element, x y coordinates of all the nodes are given here, they are put in a vector x n and y n, all the x coordinates, y coordinates. The procedure for checking or to obtain the isoparametric mapping remains same, whether it is 8 node element or 4 node element. So, same steps which we followed for 4 node element, except that now we need to take shape functions of 8 node parent element before we proceed with writing isoparametric mapping expressions. So, we need to know what are the shape functions for 8 node parent element. Shape function expressions we need to know, and how can we get this? You just go back to the table where shape functions for 4 to 9 node element are given. So, from there you can easily get this information, the shape function for this 8 node parent element in terms of s and t. So, we have all the expressions for the shape functions, we also know the coordinates, x y coordinates of the actual element. So, we can easily use this information, both the information, and we can write expressions for isoparametric mapping. X is equal to sigma n I x I goes from 1 to 8, and substituting n1 to n8, x1 to x8, and simplifying we get this expression. Similarly, y in terms of s and t. So, we got x in terms of s and t, y in terms of s and t. These are the expressions for isoparametric mapping. Once we obtain these two expressions, we can easily take partial derivatives of x with respect to s and t, y with respect to s and t, and we can easily find what is determinant of j following same procedure as what we did for 4 node element. By evaluating derivatives, the Jacobian matrix can easily be written, and once we simplify we get this expression. Now, you can see determinant of j expression is looking more complicated. So, in this case it is better we plot this with s going from -1 to 1, t going from -1 to 1. A surface plot of Jacobian can be plotted with respect to s and t, with s going from -1 to 1, t going from -1 to 1. So, this is surface plot of Jacobian, and it can be easily verified from the plot that determinant of j is greater than 0 over the entire parent element domain, that is s going from -1 to 1, t going from -1 to 1. So, mapping is fine. The other way of checking is we can also plot x y, because we know we obtained already expressions of x and y with respect to s and t. So, we can plot that, and if you compare this figure with the actual element, you can see this is similar to actual element or exactly looking same as actual element. So, mapping is fine. So, we have two evidences, one is determinant of j greater than 0 and the other one is plot of x y. So, both these evidence show that mapping is good. So, now let us see what happens if we tweak this element little bit. So, the next example is repeat the previous example. If node 2 is moved to location 7 0, that is x coordinate is 7, y coordinate is 0, making node 2 closer to node 3. So, whatever the vectors of x coordinates and y coordinates we have in that earlier node 2 is located at 4 0 location. So, now it is moved to 7 0 location, except that all the other nodes or the locations of other nodes remain same. So, the nodal coordinates get modified like this. So, with this change we can repeat the entire process following same steps as those in previous example. Determinant of J Jacobian matrix, which is determinant of J, is given by this one. So, same procedure, what we need to do is we need to plot this determinant of J with s going from -1 to 1, t going from -1 to 1, or we can plot x y, because we already know x y in terms of s and t with s going from -1 to 1, t going from -1 to 1. So, determinant of J plot looks like this. You can see from this plot determinant of J is changing sign from positive to negative. So, at some location over the domain of element, determinant of J is going to be 0. If something is changing from positive to negative or negative to positive over a particular element domain, that means at some point in that element that particular quantity takes value equal to 0. So, this plot clearly shows that there is a changing sign over the parent element domain. So, the mapping is not good, and same can also be verified by plotting x y in terms of s and t. And if you see in the right hand side bottom corner, if you see at where x is almost equal to 8, you can see a fold there. A fold can be observed. So, that shows that mapping is not good. The plot of element produced from mapping clearly shows that there is some problem with mapping. So, here wherever mapping is not good, that is, we have taken two sets of examples. One is corresponding to 4 node element, one is corresponding to 4 node quadrilateral element, the other set of examples corresponds to 8 node element, and we have seen with one particular placement of nodes mapping is good, and if I change the nodal location little bit, a mapping there is a problem with mapping is observed. Similarly, when a 4 noded element is if the sides of that particular elements are the angle between the sides of elements is very small or very large, also we have seen there is some problem with mapping. So, in the next class we will see what are the guidelines for proper modeling with isoparametric elements, guidelines for placement of nodes and also angle between the edges of elements.